Hello, my dear Bayesians. How are you doing? So today, in this short tutorial, I'm gonna show you how to choose priors under constraints. And the first one of them is that you need PyMC at least 4.0 to run this notebook, because this is a brand new function and functionality at the time of recording. Okay, so at least PyMC 4.0. So what are we gonna look at? Well, when you're a modeler, you have several problems. One of them could be that you want a gamma prior because you have positive values, or you want a beta prior because you have values between 0 and 1. But these distributions are way less intuitive to parameterize than the normal distribution. So what do you do in these cases? Another problem is that people don't understand your job, so you end up alone at the party. And actually, we won't cover that second problem here because the video would be way too long. Or it could be that you need a non-statistician to define your prior, and they will neither know nor care about whether you need a gamma or a beta. But if you ask them, they will give you an important information. And something I often do is ask non-stat people in terms of betting, because that relates very, very naturally to the Bayesian frameworks. And that helps you basically think in a way where you have to put your money where your mouth is. And so once I asked my colleague about prior for instance, the efficiency of Google Ads on revenue, she could answer me by telling me, I bet that we need to spend between $0.1 and $3 on Google Ads to get one additional sale. And I'm almost sure it's not less, but maybe it's more, okay? And that's very cool, right? That's a very cool colleague because she completely understood her framework, and also because, let's face it, my question was really good, and nudged her into that betting framework. And that way, our job as a statistician is made way easier because we can translate that information, that prior knowledge, that domain knowledge, into the statistical framework. And here, since we need positive real values, I can translate that into, I need a gamma distribution that has most of its mass, and here we'll define most of it by 95%, probability mass between 0.1 and 3. But again, 95% here is nothing magical, right? You can use any math you need. That could be 83%, 90%, anything you want. So finding a gamma distribution that fits these constraints by hand, it may take you a long time to find an appropriate combination of parameters. That's, I guess, the drawback of the flexibility of the gamma. So now we have two options. First one is despair and cry. The second one is not despair and use the new PyMC.find constraint prior function. And so we will demonstrate how to do option 1 in another video, but for now, let's choose option 2, okay? So under the hood, what's going to happen is that PyMC is going to ask SciPy's optimizer, and parenthesis, how cool is that, right? PyMC, an open source package, calling SciPy another open source package. So all of these coming to you from the free open source nerdy world. You are welcome. Hope you appreciate it. So under the hood, PyMC is going to ask SciPy's optimizer, what are the alpha and beta parameters that fit the user's constraint? Why alpha and beta? It's just that gamma distributions are parameterized with two parameters called alpha and beta traditionally, but if it were a normal distribution here, it wouldn't be alpha and beta, it would be mu and sigma, okay? So that's not very important here. But basically, what's important is the question that PyMC is going to ask SciPy's optimizer. How do we do that? Simple, we import our favorite packages, RVs, NumPy, PyMC, and then we define our constraint. So here, as you can see, we've got the mass, 95%, so that's the most of its probability mass that I talked about before. Then we have our lower bound, 0.1, our upper bound, 3, and then we just ask find constraint prior for the gamma distribution, which answers those constraints. And then we just have to pass an init guess dictionary to the function. What's that? It's just a way to initialize the SciPy optimizer, okay? Don't sweat it too much. It's just telling SciPy's optimizer, well, you should start around that region, because intuitively, if you start the optimization very far from the optimal region, well, then either it will take a long time for the optimizer to find optimal parameters, or it could even fail. So it's just nudging him, helping it a bit, and telling it, okay, just start around there, okay? So if you start having difficulties with the find constraint prior function, it may be because your initial guess is very far from the optimal region, and that way the SciPy optimizer has problems. But if that happens, and when that happens, you will see warnings here either thrown by PyMC or SciPy. So don't sweat it too much. Here, as you can see, everything is going well. We just had that weird warning. Don't worry about that. Doesn't mean anything in our case. Nothing to worry about, at least. So we run that. Everything is going well. And what do we get? We're getting back the optimized distributions parameter in that dictionary here. And when we look at that dictionary, well, what do we get? We get alpha, which should be around 2.2, and beta, which should be around 1.8. So how awesome is that, right? We asked PyMC for a gamma distribution with our constraints, and then PyMC tells us back, well, then you should use a gamma distribution with those parameters more or less, right? It's not exact, that's not what counts, it's like it's in that neighborhood. Now you may have a question, well, Alex, that's very well and good, but how do we use that in our PyMC model? Well, it's very easy because, well, you just open a model context, right, that you love by now, and you have your supermodel, and in your supermodel, you have a beautiful var, which is the gamma distribution, and you just have to unpack the dictionary that you got before. Right, over there, we've got our constraint priors, and then you just use the magic of Python dictionary unpacking by inputting ** constraint priors, and that will just give everything that PyMC needs to initiate that variable. How beautiful is that beautiful var, right? So that's awesome. And that's how you would use a constraint prior into your model. Now, you may ask, well, what does this distribution look like? Go ahead, ask it. I'm waiting for you to ask it. Okay, good, thank you. And then my answer is, well, let's draw samples from it and plot them. So how do we draw samples? Well, this is the bonus for that video. There is a new function in PyMC4, which is called pm.draw, and we just pass it our beautiful var that we created just before. And then we call pm.draw, my beautiful var, and ask it for 10,000 rows here. Save that into that variable. This is just an empire of draws. And then when you plot that, using what's important here, rvs.plot this function, you pass it the draws, and what do you get? Well, you get a distribution, a gamma 2.2, 1.8, which indeed looks like most of its mass, here it's 95%, is indeed between 0.1 and 3. And that's super cool. So we're just doing that check to understand what the distribution looks like. But of course, you understood that actually PyMC did the check for you under the hood. And actually, our constraint doesn't only seems to be respected. I am sure it is, because the math are telling us, because PyMC runs some tests in the background. So if any issue had appeared, PyMC would have warned us that our constraint was not respected. Okay, but I love looking at my priors that way because that helps me understand them and understand my models. Okay, so basically, on that note, we are done. And as always, Pym cheers and best Bayesian wishes wherever you are. And with that, I will drop my mic figuratively, not literally, because this is an expensive podcasting mic. So I hope you will understand and indulge me. And on that note, I'm going to leave you here and wishing you a good day, my dear Bayesians.